Hi everybody, this is Jim Corkins, and we are continuing on to our last section in kinematics. And this is specifically for the university students, which is Physics 121 at Mesa Community College. So like always, please do your readings, okay? Now, here are the motion equations. For these problems, we're not really going to need to know them too much, but this is all about how to use calculus to solve equations if you don't know anything else about them, okay? All right. Now, you are going to have to know differentiation, how you take a position versus time equation and turn it into an acceleration, a velocity versus time equation, and then turn that into an acceleration versus time equation. And if you're given an acceleration, figure out a velocity versus time equation from that, and then using that, integrating that again to make it a displacement equation. Okay? So let's do a couple problems here. So it looks like you're given a general form question, equation. In this case, it looks like it is a normal equation, and I'm assuming this is displacement is equal to bt squared minus ct, where b is 2 meters per second squared and c is 6.7 meters per second. And we want to know what the instantaneous velocity is when the object reaches 2.2 meters per second. So velocity is equal to displacement, a change in your displacement over a change in time. And since we're given this equation right here, x, what is this? X is going to be equal to, where x is bt squared minus ct. We're going to have to differentiate this with respect to time. So to get the instantaneous velocity, we're going to differentiate bt squared with respect to time, and we're going to separately differentiate, and I'm going to take the ct to the front. I'm going to take the negative to the front, and the ct is going to be in there, dt. Okay? Now, differentiation, again, if you haven't watched the video 1.8 in this series, please go back there and do so, because that's where I kind of review differentiation and integration with respect to time. Okay? So in this case, what's going to is right here, we're going to go ahead and put, we're going to take the b to the front. So we're going to multiply this. Differential, we're going to take that 2, which is n, to the front. T to the 2 minus 1. Minus c, we're going to bring to the front. T to the first, we're going to multiply this by 1. T to the 0 minus 1. So this is going to be 2b t minus c. All right, so now we're going to plug in our numbers. B, which is the acceleration, is going to be 2 meters per second squared times the time, which is 2.2 seconds, minus c, which is 6.7 meters per second. So the velocity at 2.2, this should be 2.2 seconds. So what is that? That's going to be 2.2 times 2 times 2 minus 6.7. 2.1 meters per second. So that's how fast it's moving. 2.1 meters per second at that moment in time. Okay? Now, this part of the problem, they want to know what is the acceleration of the object. And it's the same problem. We want to know what the acceleration of the object is when it's at 2.2. Well, what we have to do is we have to do this twice. We have to take the first derivative of this with respect to time, and then later on we're going to have to take the derivative of the velocity with respect to time. Okay? And so we just did this derivative with respect to time, and we got a velocity that was 2bt minus c. Well, now let's just do this again to get the acceleration. So we're going to have to take that velocity equation and do this derivative here, which is 2bt minus c. And we're going to differentiate that one with respect to time. So when we do that, we're going to take derivative of 2bt dt minus dc over dt. Okay. I'm going to take the 2bt to the front, and I'm going to take just the 2b to the front, and then we're going to multiply this. So the t to the first, the 1 is going to go here, and this is going to be t to the 1 minus 1. That looks weird. That looks like an h. 1 minus 1 minus c, and this is going to be, we're going to differentiate t to the 0th over dt, which t to the 0 is just 1, so 1 times negative c. Anyways, when we get to this, what we end up with is 2b times 1 times 1, and then c is going to be, take the 0 times t to the 0 minus 1. So when we do all that, what we end up getting is just 2b. That's going to be the acceleration, because this is 0. So this is going to be, so that's going to be 2 times 2 meters per second squared, which is going to be 4 meters per second squared. Okay. All right, so that's how functions can change things. This does make sense, by the way, because in a quadratic equation, I know that seems weird, but if we have delta x, which is 1/2 a delta t squared plus vi delta t, they said that b is just bt squared. So this is b, this thing is b, and this is going to be c, right? So if b is equal to 1/2 times the acceleration, then 2 times b has got to be equal to the acceleration. That's another way of doing this without actually doing derivatives in calculus. All right? And where c is just equal to the initial velocity. So, anyways, moving right along. Now, suppose we are given this right here, a velocity that is, so we're given an equation of velocity is equal to bt squared minus ct. So this is a curvilinear, this would be a curvilinear velocity equation, right? So this is weird, right? In fact, in a velocity equation, which is a delta t minus the initial velocity, this c is actually going to be our acceleration. Okay? This b is going to be a jerk, which is a j. So again, a jerk is a second order part of the velocity equation where there is a change in your acceleration. So this right here is kind of like a change in your acceleration over time. So that's what a jerk is. I should have written this over here. A jerk is a change in your acceleration over time. And I don't know why I put a hat on this, because it's a vector just like this. So this is a j vector. Anyways, so this is weird. We don't run into a lot of problems in our class where you have a change in your acceleration. Most of the time we're just doing an acceleration. But in real life, there are problems where you do have second order velocity equations. So, okay, so the acceleration is that, this is a jerk. So anyways, the question is asking, we need the total displacement in between this time frame. Okay, essentially it's asking us for what is the area underneath the curve that is of this line. So this line is making a line with respect to the velocity equals 0 t-axis, and we need that area underneath that line relative to that. So let's do this. So velocity is going to be equal to dx dt. So we start it just like we regularly do, where this velocity equation is bt squared minus ct. Okay. I have a feeling this is going to be t to the third, and this is going to end up being t squared. So dx is going to be equal to bt squared minus ct, and that's dt. So we're going to take that dt and multiply it through. dt minus ct, we've got c a little bit bigger, dt. Now we're going to have to integrate these guys, x initial to x final. And we're going to integrate these guys, and it said from 0 to 2 seconds, and 0 to 2 seconds. I'm not putting in the numbers in yet for b and c. It's just easier to do the integration on this. When we do that, our x is going to go from x initial to x final, because that's just the general form. We have to put limits on this. B is going to be multiplied by, this is going to be 1 over 3, so which is going to be at 1 over n plus 1, which is 2 plus 1, times t to the n plus 1, which is 2 plus 1, which is the third. And this is going from 0 seconds to 2 seconds. You know what? I'll write that out. I don't want to skip steps. So this is 2 plus 1 times t to the 2 plus 1. 0 seconds to 2 seconds. And this is going to be minus c, and this is going to be times 1 over 1 plus 1, because it's t to the first right there, t to the 1 plus 1 from 0 seconds to 2 seconds. So this is x final minus x initial. We subbed in those for there. This is going to be b and this is going to be b, so this is going to be 1/3 b t to the third, just cleaning this up. So I'm going to bring the numbers to the front, so 1/3 to the front, b t to the third, 0 seconds to 2 seconds, minus 1/2 c t squared, 0 seconds to 2 seconds, so x final minus x initial is just going to be delta x. This is going to be 1/3 b, this is going to be 2 seconds minus 0 seconds that we're going to end up cubing, minus, that looks weird, minus 1/2 c 2 seconds minus 0 seconds squared, which is delta x here. So 2 squared is 8. So here now we're going to put it in our numbers. So this is going to be 1/3 times 4.2 meters per second, and that should probably be cubed right there. That doesn't make sense that that's meters per second there. That should be meters per second cubed, times 8 seconds squared, so cubed times 8 seconds cubed, so 2 times 2 times 2, minus 1/2 c, which is 3.2 meters per second, and that should be squared, that's an acceleration, times 4 seconds squared. Okay, so the seconds cubed is going to cancel out with seconds cubed, seconds squared is going to cancel out with seconds squared, so we're going to get a delta x that is going to be equal to, let's do all this, 4.2 times 0.5 times 8 equals 16.8, minus parentheses 0.5. Whoop, hold on, I'm gonna just double check something. 0. You know what? 1 divided by 3. 1 divided by 3 equal, come on, 1 divided by 3 times 4.2 times 8. Okay, 11.2, that makes more sense. Minus parentheses 0.5 times 3.2 times 4, and parentheses equals 4.8. So this, whatever this object is, it's going to be displaced a total of 4.8 meters. Okay, let's do the last one here. Which looks like it's equal to the first one. Yeah, I think we're actually done. Okay. Well, I hope you enjoyed this. And remember, please do the readings, okay? And this was using calculus to solve application problems. All right, have a good day. Bye.